In this lesson, we will solve a classic thermodynamics problem about entropy change in a free expansion. The problem says, find the entropy change for the free expansion of 0.75 moles of an ideal gas from V1 equals 1.5 liters to V2 equals 3 liters. We'll build an intuitive picture first, then derive the formula and compute the answer step by step. Let's build an intuitive visual. Imagine a rigid, thermally insulated container with a removable partition in the middle. At the start, the gas is confined to the left side, volume V1, while the right side is vacuum. When we remove the partition, the gas expands freely to fill the whole container, reaching volume V2. We'll draw the container and the partition. We'll label the left side as V1 equals 1.5 liters, and the right side as vacuum initially. Now, let's sprinkle gas molecules on the left side only. Next, we remove the partition. The gas spreads out to occupy the whole space spontaneously. No external work is done, and no heat is exchanged. Now, the key thermodynamic facts for a free expansion of an ideal gas are: no work is done on the surroundings, W equals 0, because the external pressure is 0. No heat flows, Q equals 0, since the container is insulated. So the change in internal energy is 0, delta U equals 0. For an ideal gas, internal energy depends only on temperature. So delta U equals 0 implies the temperature does not change. But this real process is irreversible. So to compute entropy change, we imagine a reversible path between the same end states. The convenient reversible path is an isothermal reversible expansion from V1 to V2. Let's put those ideas on screen. And now, write the isothermal reversible entropy change. Now, we simply substitute the numbers. N equals 0.75 moles, V1 equals 1.5 liters, and V2 equals 3 liters. The ratio V2 over V1 is 2. So delta S equals N are times the natural log of 2. Let's write that substitution. We compute the natural log of 2, approximately 0.693, multiply by R equals 8.314 joules per mole Kelvin, and by 0.75 moles to get the final number. We'll present the result with proper units. So the entropy change of the gas is about 4.32 joules per Kelvin, positive as expected. In a free expansion into vacuum, the surroundings do not exchange heat, so the surroundings entropy change is approximately 0. The system's entropy increases, so the total entropy of the universe increases. This captures the irreversibility of the process. Visually, as the gas spreads from the left half to fill the entire container, the number of accessible microstates increases, which corresponds to an increase in entropy. That is why the entropy change is positive.